Okay, welcoming you all to a new discussion. Today's topic of this discussion is law of indices. So we'll be looking into the most fundamental laws of indices which comes in algebra, and appropriately you'll be discussing some examples related to each of these laws, and just to get an understanding how the laws applies in algebraic simplifications. So before we start, the important thing that we all should know is about a power value. So if I give you an example, a to the power b, right? So this is what we call a power value. So what you all can see here is a value. So in this value, this a is said to be the base of the value, and the b on top is called the index, right? And then if you consider all these two symbols together, we call it the power of a. That is the power value, power of a, right? So as the most fundamental thing or the base, we should know this part before we move into the discussion of the laws of indices, right? So this is called the power of a. The lower part is called the base of the value, and the top uh, b on top of a, or we call a to the power b. When it comes to that, b is the index. So let's move into the first law. As you can see now, we have on the screen a to the power m times a to the power n is equal to a to the power m plus n. So which means that if you see a multiplication between two values consisting the same base, the two indexes can be added together. So here you all can see the first value is a to the power m, so the base is a. Second value is a to the power n, again the base is a. The two cases are being multiplied. So according to the first law of indices, this m as the first index, n as a second index can be added together. So finalizing can be done by a to the power m plus n altogether, right? So if I take an example, we can say x to the power 2 times x to the power 5, right? The first example. So then we can rewrite this as just a single x, and as the index we can take these two values, index values, and add them together because the two bases are the same. So 2 plus 5, and what we get is x to the power 7. 2 plus 5 is 7, right? Another example, we can say a to the power x times a to the power y will end up giving us a to the power x plus y. So you all can see that the index of this situation is a expression, right? Algebraic expression. So a to the power x plus y, a to the power an algebraic expression. So you all might see these sort of examples. Just another one. If we take a to the power x plus y times a to the power x plus z, right? So in this case, what we have to do is again the same application. The two indexes can be added together since the two bases are the same, right? So what we have to do is write the expression x plus y first, that thing plus x plus z. So end of the day what you get is x plus y plus x and plus z, and a to the power 2x plus y plus z, right? So we'll be getting another expression. So there can be situations like this. Moreover, if I take another example with a bit of fractions, let's say m to the power half times m to the power 1 over 3, for example. So then what we can do here is we can get m as the common base, half plus 1 over 3, because the two indexes can be added. So half plus 1 over 3. What you get is, if I just do the rough work here, you all know when you have this sort of a situation, we get the LCM as 6. Then this side will become 6 divided by 2, 3. 3 times 1 is 3, plus 6 divided by 3 is 2. 2 times 1 is 2. So end of the day you will be getting 5 divided by 6. So this part will become m to the power 5 divided by 6, right? So we can get things done the way that the rule says us, right? So this is the first law of indices. The second law, as you all can see, previous case was the multiplication between the two power values consisting the same base. The second law shows that the division between the two power values consisting the same base. If you can see that there is a power value divided by another power value having the same base, what we can do is we can subtract the indices or the indexes, right? The numerator index subtraction denominator index, or from the other side we can say the denominator index can be subtracted by the numerator index. So a to the power m divided by a to the power n. So we can rewrite that as the application of the second law, a to the power m minus n. So in this case, m is the index of the numerator, n is the index of the denominator. So m minus n, right? For example, we can say a to the power 8 divided by a to the power 2. So we'll be getting a to the power 8 minus 2. Very simple, which is a to the power 6, right? Another example, let me say x to the power 2 plus y divided by x to the power 1 plus z, right? Something like this. So we can get it finalized by applying the rule x to the power 2 plus y minus 1 plus z, right? Then you have to be careful, there's a little bit of simplification here. X to the power 2 plus y minus 1 times positive 1 will become negative 1, or negative 1 times positive z will become negative z. So what comes as the final answer is 2 minus 1 is 1 plus y minus z, right? We can get things done in that way. Just another example with a fraction, a to the power half divided by a to the power 1/4. So we can rewrite this as a to the power half minus 1/4 or quarter. So we'll be getting 2 minus 1. Answer is a to the power 1 over 4, right? Just the application of the second law. So let's go into some examples, some more examples. So as you can see here, in this case we have one term multiplied by another term, each term consisting three symbols, right? So here we can see a to the power 3 into b to the power 2 into c times a to the power 1 into b to the power 3 into c to the power 5. So what we can do here is little bit of rearrangement by expanding the given line a little bit more to show what's going on in between each term or in between each factor. Right. So here you all can see a to the power 3 and there's another a to the power 1 which are the same bases. What we can do is we can write them together since everything is connected with a multiplication sign. So a to the power 3 times a to the power 1. Then we have b to the power 2 and a b to the power 3. So b to the power 2 times b to the power 3 together times c to the power 1 and another c to the power 5. Right. Now let's take the a's first. So a to the power, same base, two indexes to be added because it's multiplying. So 3 plus 1. Then times we have b. So just a 1b from these two. We have 2 and 3. So 2 plus 3. No problem because there's multiplication in the middle. Then we have times c. Two c's multiplying together. So we get 1 plus 5 as the index of the second c. So finalization will be a to the power 4 times b to the power 5 times c to the power 6. Right? So a to the power 4, b to the power 5, c to the power 6 can be written all together without the multiplication signature. So this is the final answer. Next example to apply the same rule, which is the first one, but with a bit of fractions can be seen on the indexes. So here also you all can see a, b, c to connected together as the first section of the expression, and we have again an a, b, c connected together as the second part of the expression. So what we are going to do again is to do a little bit of expansion to give you a clear understanding of what's going on. Negative 2. So here we have to be careful. C to the power negative. The power is a negative power. So there's no problem. We can simply write it as negative 2. A to the power 1 divided by 6 into b to the power 1 divided by 2 into c. So again, as the previous, we have the two a components can be written together. So a to the power half into a to the power 1 over 6 into b to the power 2 times b to the power half into c to the power negative 2 times c to the power 1. So from a we get 1 over 2 plus 1 over 6 times 2 plus 1 over b to the power 2 plus 1 over 2 times c to the power negative 2 plus 1 from here. So in this case, we'll be getting a to the power 4 divided by 6. If you get the LCM 6, we get 2 3's. So 3 times 1 is 3, 3 plus 1 is 4. So you get the numerator 4, denominator 6 as the LCM. B to the power 5 divided by 2, right? And c to the power negative 2 positive 1 will become negative 1. So the end result can be seen as this is here. It's a little bit of let me say a simplification. We can simplify this as 2 times 2, 2 times 3. Here we are going to simplify it further. So what we are getting now is a to the power 2 divided by 3, b to the power 5 divided by 2, and c to the power negative 1, right? But in a later case, when we have a negative index, we can further go one step and rewrite this as a to the power 2 divided by 3, b to the power 5 divided by 2, and the negative index component can be taken down the line as a denominator, at that time the index negative value will become positive. So c to the power positive 1. So this also can be written later after the discussion of that particular law. So we will be talking about that law a little later. Right. So one step further, again to apply the same sort of thing with the second index law, since you all can see here in between A and A's there's a division, in between the B's we see a division, in between C's we see a division, right? So if I rewrite this same expression in a way, in this a to the power 3 times b to the power 2 times c to the power 4 divided by a times b times c to the power negative 2, right? C to the power negative 2. Since the numerator and denominator you don't see any positive and negative signature, but we see multiplication, so there is no problem dividing now since we have multiplication in the both parties. So you all can see here a to the power 3 divided by a, we are going to separate this bigger fraction into three portions since we have three symbols. Then we get the b part, b to the power 2 divided by b times c to the power 4 divided by c to the power negative 2. So bit of a separation. Now the application of the second law, when we see division between the power values consisting the same base, indexes will subtract. So a to the power 3 minus 1, underneath you get a to the power 1 times b to the power 2 is the index of the numerator, then the denominator b to the power 1, so 2 minus 1, and when it comes to c we have the numerator index c to the power 4, 4 minus, and at the denominator to be careful, that is a minus 2, so 4 minus minus 2, so you get two minuses. You have to be careful in that. We can simply use a bracket for the separation, so then no confusions, we can get it everything sorted without any mistakes, without any errors. So a bit of simplification, a into a to the power 3 minus 1 is 2 times b to the power 2 minus 1 is 1, and in this case c to the power negative times negative becomes positive. So in this case you will see c to the power 4 positive 2, because these two negatives multiply and make it a positive. So 4 c to the power 4 plus 2, right? 4 plus 2 will become 6, so the final answer is 6. End of the day we get a to the power 2 b c to the power 6. This is the final answer, right? So hope that point is clear. The 2 points, the two first laws are clear with you all. Another example to apply the same thing, but you all can see here the indexes are having some fractions, so that is to be simplified by using the second index laws, first and the second, but bit of more simplification since we have fractions to deal with. So if I do the same operation as I done previously, p to the power half times q to the power 2 times r to the power 2 divided by 3 divided by p to the, excuse me, right, p to the power 1 over 4, q to the power 1 over 2, and r to the power 1 over 6. So again what we can do is separate this bigger fraction into three portions. P to the power half divided by p to the power 1 over 4 times q to the power 2 divided by q to the power 1 over 2 times r to the power 2 over 3 divided by r to the power 1 over 6. So then we get p to the power 1 over 2 minus, because of the division, you get the minuses between the indexes, times q to the power 2 minus half into r to the power 2 over 3 minus 1 over 6. So you have to slowly get the indexes simplified. So what we get here will be again LCM of 2 and 4 is 4. So we'll be getting 2 here, 2 plus 2 minus 1 is 1. So we get 1 over 4. Half minus quarter is a quarter. Half is 2 quarters. So half minus quarter is a quarter. Times q, we get 2 minus half. 2 minus half is 1 and half, means 3 divided by 2, right? So if you simplify this slowly in a rough paper, you will see that it's 3 divided by 2, right? Then the r indexes, we have 3 and 6. So 6 is the LCM. We get 4, because 3 times 2 is 6, 2 times 2 is 4, 4 minus 1 is 3, right? So a bit of a simplification here. 3 times 1, 3 times 2. So end result will be p to the power 1 over 4, q to the power 3 over 2, and r to the power 1 over 2. So this is the final answer in that. Moving to the third law of indices. We discussed the first two, now the next one. So here what we have to understand is, we call it a power of a power. So earlier in the very first thing we discussed is about a power value. So we understood that when it comes to a power value, there is a base component and an index component. Now in this case, you all can see there is a power value inside the bracket further being powered. So this is what we call a power of a power, right? Power of a power. So when you see a power of a power in this format, what we can easily do is take the two indexes, the internal component and the external component of the indexes, we can multiply them together, as you can see here. So a to the power 1 to the power n, a to the power m to the power n is equal to a to the power m times n. Now just an example, if you get a to the power 2 again to the power 3, if you get this, we can rewrite this as a to the power 2 times 3, end of the day it is a to the power 6, right? And if you get x to the power half times 2, right? X to the power half again to the power 2, right? This is the outside one. So internal component, external component. So we have two power components. So what to be done according to the rule, x to the power half times 2. What happens here? When you get this sort of a situation, we can simplify. This 2 and this 2 cancels. End of the day what we get is x to the power 1 means x, right? This is example number 2. Then we have example number 3. We can take a to the power x to the power 4. A to the power x to the power 4. End of the day it will become x times 4. So a to the power 4x, right? Something like that. So we can get used to this. It's quite simple to understand and easy to keep them by hearted, right? So let's go and see what's next, right? Then we have a example to apply the law number 3. So here, if I rewrite this bit larger for you all to understand, what we get here is p to the power 3, the whole thing to the power half, times q to the power 2 and the whole thing to the power 4. So external component is 4. In the first term, the external component is half. So what we can do here is we can first take the p part. P is 3 times 1 half. The whole thing times q to the power 2 times 4. So end of the day, what we get is p to the power 3 divided by 2 and q to the power 8. So we can finalize it as p to the power 3 divided by 2 q to the power 8. Right? Sorry about the lines, power 8. So hope that point is clear. Right? So if I rewrite this here again, sorry about the technical issues. Right? So this is the answer. Okay. Another example to apply the same. So here you all can see we have to use the whole 3 laws that we have discussed so far, right? The first rule, the second law, and the third one. So we have to apply everything here to solve this thing out. Let's work it out little. M times n to the power 2 times 3. If I write this, the numerator component in this way, which is wrong, which is not right, right? This you should not write like this. Should not write like this. So the right way of doing it is, first you have to understand the component within the brackets, because this outer power, the external power component, is common to all the individual components inside the bracket. So this power 3, external power 3, is common to the m as an individual factor, and again common to n to the power 2 as an individual factor. So if I rewrite this in the right way, I should write it in this way, right? So m n to the power 2 whole thing to the power 3 means, right, which means I should write it here, m to the power 3 times n to the power 2 times 3. This is how it comes, because this outer 3 is common to the both cases. You have to be careful in that, right? Okay, so let's get the thing done. So same in this part as well. If I use a different color for that, you all can see m to the power half and n to the power 1 over 4, the whole thing to the power 4. So this 4 is common to m and n. So if you write it correctly, this is how it has to be. Half times 4, right, will becomes 4 divided by 2 into n. Again, quarter times 4 will become 4 divided by 4. This is how it has to be. So this 4 is common to both parties. Right, so now with that knowledge, if we go and do the simplification, we'll be getting m to the power 3 times n to the power 6 with the multiplication divided by m to the power 4 divided by 2 is 2 into n to the power 4 divided by 4 is 1. Right, so end of the day, m to the power 3 divided by m to the power 2 into n to the power 6 divided by n, and m 3 minus 2 times n 6 minus 1. The answer will be m to the power 1 n to the power 5, or else m n to the power 5. Okay. Hope everything is clear up to this point. The next law, right? Yeah, this has to be the fourth one, third. Here we have the fourth law. Let's discuss a little about the fourth law, or just don't get confused with the law number. We'll first discuss this one. So this has to be the fourth law. If you see a power value with a negative index, right, in this law it discusses about a power value with a negative index, which means a negative power value. We can write it in an inverse format, which means that negative index, negative power can be taken below the line, which makes the negative becomes positive, which means the existing signature, existing negative or positive signature will change when you change the position of the particular power, right? Now, for example, in this case, you all can see a to the power negative n has taken down the line as to a denominator as an inverse 1 over a to the power n. So, in that case, you can see that the negative signature vanishes. It has disappeared. It has become positive. So, the other side, in the reverse operation, if you say b to the power, let me say x, can be written as 1 over b to the power negative x according to our requirement. So that also possible. A negative index in any case, right, in case of any requirement, if you need to generate a component with a negative x index, what you can do is take the inverse, take it down the line. So b to the power x can be written as 1 over b to the power negative x. So that also possible. You all can take each law vice versa, right, in both direction. There is no only a one specific direction to observe or use this. Wherever in case of the requirement, we can make it use in both directions, right? For example, now let me say if we have 2 to the power negative 4, right, we can rewrite this instead of taking 2 to the power negative 4, instead of worrying about finding the answer, we can rewrite this as 2 to the power positive 4. Right, the answer is end of the day 1 over 2 to the power 4 is 16, right? So answer is 1 over 16, finalized. Very simple. Okay, so this is another very important law of indices that everybody should learn and use it in further algebra as well as in all other mathematical simplifications or derivations. We will be meeting these sort of situations every time we do mathematics. So knowing this rule is really important. Taking the inverse of a particular existing power value, right? So there is not much to discuss in this. Let's go one step further. We have the fifth, right? Let's take this as the fifth rule. Now, if you can see a fraction as the index of any power value, that can be written in another format, right? That can be written in another format by referring to a root sign, right? By referring to a root sign. So in this case, note that we were referring to this signature just itself. Now, what is the meaning of this? We call it the square root of, this is equal to square root of 4. This is how we explain this. Square root of 4, right? Square root of 4, which is equal to 2. We all know this. This is quite basics. Now, if we see this, a small 3 here, we know that we need to take the root 3 of 8, right? This is not the square, this is not giving us the meaning of square root. This is what we call the cubic root, right? This is called cubic root of the value 8, which is again 2. Why? 8 is equal to 2 times 2 times 2, right? This is the reason. Here 4 is equal to 2 times 2. So that is the square root. This is referring to a square value. The cubes refers to cubes. You all know that, it's quite basics, right? So here, how to get the uh, volume of this sort of a cube is, we are going to multiply the each side, right? Length into breadth into height, or length into width into height. So 3 times multiplication. So 2 times 2 times 2, end of the day it becomes 8. So the cubic root of 8 is 2. So we all know these three very basic situations. So in this case, you all should know that the meaning, the index meaning of these two, we can rewrite the same component with different formations. Now square root of 4, you don't see any value here, but in the cubic root we specifically put 3 to say that it is cubic root. Likewise, we might find the fifth root value of x, for example. So let's go and see how we can rewrite that in a index format. So the meaning of this, we can write it as 4 to the power half, right? 4 to the power half. The meaning of this, if you convert this to the index format, we can say 8 to the power 1 divided by 3. Always the denominator of the factor, index factor, denominator of the factor index is telling us which root that we have to take. Now in this case, we can write x to the power 1 over 5, right? So this is the story here. So you all can see a to the power m divided by n, a to the power m divided by n. So in our examples, m is 1 always. You all can see that the numerator part of the index is 1. So m is 1. But the n value varies. So the first one, n is equal to 2. In the second case, n is equal to 3. Third case, n is equal to 5. So where should this n value goes? You all can see on this case, n comes next to the root sign, saying that which root that we have to take off, right? Is it a cubic root or a square root or any other root value? Okay. M is the index of the power, index of that particular base. So m belongs to always the power value, right? So here you all can see 4 to the power 1 divided by 2, 8 to the power 1 divided by 3. So inside what you always have is 8 to the power 1, 4 to the power 1, x to the power 1. That is why you get 1 over 5. So for another example, if you take x to the power y, the root of the sixth root of x to the power y, we can write x to the power y divided by 6. Okay, so this is the meaning. So the law shows that if you have a fraction as the index, the numerator of the fraction goes as the power value index. Inside the root sign, the denominator value gives us the idea about the value of the root, which root value that we have to take, right? So this is the other very important index rule that we have to understand, right? So here the final rule for the day, the sixth rule. If you see a power value consisting an index 0 which is equal to 1, right? Now for example, if I say 10 to the power 0, answer is 1, right? Or b to the power 0, answer is 1. If we say if we just see something like x to the power 2 minus 2, right? X to the power 2 minus 2 in a situation, this will be equal to x to the power 0. End of the day, the answer is 1, which is not x to the power 1 but just 1. So 0 power, right? Any value to the power 0 is always taken as 1. So that is another important rule that you all need to know in the case of simplifications in algebra and further mathematics. Okay, so here we have an example to get some simplifications done. Just see whether you all can do this. If you want, you can pause the video and give a little try out. Being honest to yourself, just take down this question in a paper and just give a try out to see whether we can simplify this. So this is not a direct application of index laws, but some algebraic expression to solve or to simplify. But in this simplification process, we'll be needing the knowledge of index rules or index laws, or we call the laws of indices. We can use that knowledge, that skill in the case of simplifying this. So these are some application type of examples that we are going to discuss now. So you will see how that we can apply the laws that you learned so far in general simplification, especially in algebra and other further mathematics. Okay, so pause the video and just give a try. I'll keep continuing. So if you get this, how to get this thing sorted, right? Now, for example, you all know, if I take a little bit of basics, we have a plus b as a value, then the whole component is being divided by x, right? For example, so we know from basic arithmetics knowledge or the mathematics knowledge, or we call the algebra knowledge, in this sort of a situation, this x as the denominator is common to both a and b. So here we can write it in a separated manner. A divided by x, then we have a plus sign, b divided by x. Why that we can write this? Because this x is common denominator for both parties, the both components, right? So you all can see that arrangement here. So there is no any problem doing this. X to the power 2, y to the power 3, that component divided by x and y, then we have a positive signature in the middle. Next component is xy to the power 2, again dividing by the same component xy. So why that we did this? Because this xy here is common for both parties or the both components. There's no harm doing this, right? So now you all know. Now I'll take you a little bit away from our ordinary simplifications. So here you all can see x to the power 2 divided by x. The ordinary way of doing it is we take x and applying our second law and saying that the numerator index minus denominator index. So then you get x to the power 1. This is the ordinary method of doing it. But by knowing that this applies, we can further do it in this way. When you see x to the power 2 divided by x, we can cancel this out in this manner. You all can see x to the power 1. So this x cancels with a 1x here, right? Cancels with a 1x here. Remaining will be 1. So answer is this existing x to the power 1. So both answers are the same, right? Similarly, if I take this y to the power 3 divided by y, again the same thing. Ordinary way of doing it is 3 minus 1, end of the day, y to the power 2. But the other method of doing it is y to the power 3 divided by y. 1y cancels with a y here, remaining is 2. End of the day, you again get y to the power 2. Right? So by knowing this basics, we'll get to directly use it in our simplification. So now you all know that there is such an index law. And then you learned about the law. You were doing a little bit of examples to practice the application of law. But with that knowledge, now you go for a little bit of further simplification in a, in different short methods. So this is some sort of a short method that we can practice. So I want you all to learn that here and practice them during all your algebraic simplification. So I'll do it for you now. One x cancels with an x here, and a 1y cancels, this y cancels with a y here, so remaining is 2. And if I do the same here with y, this y cancels with a 1y here, and this x cancels with the entire x here. So now what's remaining? Let's see the remainings. Right? In the first component, you all can see 1x is remaining here because 1x cancels with a 1x on top. If I further do it and show, right, now here x to the power 2 divided by x means x times x divided by x. So this x and this x cancels, 1x remaining. Y to the power 3 divided by y means y times y times y divided by y. So this y and this y cancels, you get 2 y's. End of the day, it's y to the power 2. This is another method. So by knowing the background, what's happening behind the screen, try to always do the straightforward method, so that will save your time and make it a bit speedier, right? So if you are doing this for training, this for examinations, these short methods will give a lot of advantage in the case of saving your time, right? So I want you all to learn this and practice. So now what happens here, we have a 1x remaining and 2y's remaining. So y to the power 2, there is no any denominator because here 1 and 1 into 1 is 1. So something divided by 1 is that the same thing, so we don't want to write any denominator. The plus sign remain as the same. In this case, x and x both cancelled, so you don't find any x components, but here we have just a 1y component remaining, so plus y. Okay, so x, y to the power 2 plus y. We can keep the answer as it is, or else we can go one step further, because you all can see that in both cases we have y as a common factor. We can remove that out. So we take the common y out, then what we have here is xy to the power 2. When you take a 1y out, the remaining will be x and another 1y. When you take this existing y out, what remains here is 1. So this is the finalized answer. Okay, so bit of a further simplification, short methods by understanding and applying the index law. So you know the background based on what's going on, based on index laws, you know what's going on behind the screen, but you do apply short simplification methods in the case of saving your time in your simplifications, right? So this is completed. Now let's move to another question. Now this is a bit tricky compared to the one we discussed. If you try to get this thing sorted the way that we did the previous, this will not give you a chance of solving it in that way. But if you just think a little bit, wisely, you will find a way of doing it, right? None other than applying index laws, the same method, but the question is a bit tricky. So I again want you to pause the video, take down the question and give a honest try out, and check the answers with the discussion. So in this case, you all can see that now it is something like, let me say, a divided by x plus y, right? Something like that. So here we can say that a is common to both x and y. There is no such way of simplifying or such argument. A is not common to, nobody can write it in this way, a divided by x plus a divided by y. If you write it, that's wrong, right? We cannot do that, right? A is not common, it's not a common case, it's the numerator. Denominator is a function, this time denominator is an expression. So there is nothing for us to do in this sort of a situation, right? But here what you all need to look into is component wise. So here we have a one component, then we have two components. If you check each component, what you can find is common terms. In every component you see an x term and a y term, which means this x and y multiplication or the product of xy can be seen in all parties, right? This product, xy product, can be seen, right? Xy product can be seen in all components, can be seen in all components. You can see, so this is the hint, this xy is the hint. So what we can do here is we take x to the power 2y as the numerator component, we divide that from xy, right? Because xy is common for all parties, so we identify the common factor and divide each component in this bigger fraction by that common factor xy. Okay, so then we get the ordinary division, the bigger division sign. Underneath we have xy to the power 2 minus xy. Each term will be again divided by the same common factor xy, right? This is a one method of doing it, xy. So then now that our simplification, short method of simplification, each term can be separately addressed, right? Now I'm going to show that x times 1, this y and this y cancels, right? What you have on top now is just x remaining, x divided by 1 remaining. Underneath, this x and this x cancels out, no x remainings, but this y cancels with a 1y. So here we have a y component divided by 1 remaining, minus x and x cancels, y and y cancels. So it is 1 divided by 1. End of the day we get 1. 1 divided by 1 is 1. So y minus 1. So if I finalize this, what we get is x divided by 1 is x, y divided by 1 is y minus 1. So this is the final answer, right? This will be the final answer. If I do this, try out doing this in another method, let me say method 2, right? This is method 1. There's another method you can try out. Some people might see the same thing in that manner. If I rewrite this, x to the power 2y divided by xy to the power 2 minus xy. If you try to understand the common factor of this expression underneath, we can remove that common factor out. What is the common factor? Both has x and y. So I'm going to remove x, y out. Sorry, forget about that. Let's take x to the power 2y divided by, I'm removing xy. So when you remove xy from xy to the power 2, what comes is just a 1y. Now multiply and see, you get x to the power xy to the power 2. xy to the power 1 times y, xy to the power 2. So there is no harm done removing xy and putting y here. Minus, when you remove xy from this component here, that becomes 1. Okay, close the brackets. So since you have a multiplication sign here, we can do the ordinary cancellation. So this x cancels with the 1x here, this y cancels with this y here. So what comes at the end of this simplification is just the 1x here divided by nothing has in this xy, only y minus 1 is remaining, right? So this is another method of doing it. So this is another good example of applying the index laws and moreover some short simplification methods. So let's move to another example. This is quite more detailed because we will get a chance of applying some further index laws that we learn later, right? So let me say, now try to understand these separately. We have let me take a dark color. We have x to the power 2, y to the power half, and right, let me say x to the power, this signature says nothing, no value here, means this is square root, right? This is square root. No value near the root sign says it's square root, which means x to the power 1 divided by 2, right? We have x to the power 1 here, 2 here. So x to the power 1 divided by 2. So in this case we have, I'll rewrite the question, never mind, times cubic root of y to the power 2, and we have x to the power 5, y to the power 3, the whole thing to the power half, right? This is in the denominator, you all can see this half is a common index for both x and y. Now x to the power 2, y to the power half times x to the power half. You all can see the root sign, square root sign is x to the power half, times, there's another example, cubic root to the power cubic root of y to the power 2. So we will be getting y to the power 2. From this 3 we get a fraction 2 divided by 3. So here we are applying that y to the power 2 divided by 3. The whole thing will be divided by x to the power 5 times half, right? Our fourth index law, multiplication, the third index law, taking the power of a power, is half here, index here outside is common for both parties. So x to the power 5 times half into y to the power 3 times half, right? So first we'll simplify this. Now here on the numerator you can see two x components, power of x, same base, application of the first rule, multiplication. So 2 plus half times y to the power half plus 2 over 3. Same base, multiply, so indexes are added. Underneath you get x to the power 5 divided by 2, 5 times half means 5 divided by 2, into y to the power 3 times half means 3 divided by 2. Okay, now again we get the application, we get to apply the second rule. Now if I take this further here, we can say x to the power 2 divided by 2 divided by x to the power 5 divided by 2 into y to the power 3 plus 2, 5 divided by 6. When you simplify this bracket here, it will become 5 divided by 6 divided by y to the power 3 divided by 2. So then we get x 2 divided by 2 is 1 minus 5 divided by 2, because it's a division, indexes subtracts. Then we have y to the power 5 divided by 6 minus 3 divided by 2. So end of the day, x to the power negative 3 divided by 2, right? So when you 1 minus 5 divided by 2, if you get 2 as the LCM, least common multiple, this part becomes 2, positive 2, negative 5 will become negative 3 underneath 2, times y to the power, LCM is 6, this becomes 9, because if you divide 6 from 2, it's 3, 3 times 3, 9, negative 9, positive 5 is negative 4, right? So bit of simplification here, 2 times 3, 2 times 2. So we have negative 2 here, negative 2 divided by 3. So x to the power negative 3 divided by 2 times y to the power negative 2 divided by 3. Now we can finalize this answer by getting the inverse, because having a negative index, if you think that it is not appropriate, what we can do is we can take the index of both parties. So x to the power positive 3 divided by 2, y to the power positive 2 divided by 3. So we took the inverse of both, 1 over 1 over, so the index become positive end of the day. So this is the finalized answer. Okay, so in the final example, you all see that during the simplification we were using almost all the index rules that we saw today. Instead of the zeroth power, all the other rules were being using in this simplification. So I hope you understood something from this video. So thanks for listening. Stay connected with the channel. If you haven't subscribed yet, please subscribe the channel and press the bell button for further videos. So thanks for listening and good luck to all of you.